Physical Science 20, Heat Lesson 3, the heat of mixtures. This is the lesson that goes along with the H5 assignment. In a closed system, when two materials are added together, the heat gained by one material will equal the heat lost by the other material. This means that the two values, heat lost and heat gained, added together will add to 0. So heat loss plus heat gained equals 0. This means that some heat values, symbolized by Q, will be positive and some will be negative. So when added together, they come out to 0. If Q equals mc delta T, the sign Q will take will be mathematically determined by the delta T value. If TF subtract TI is positive, then Q will be positive. And if TF subtract TI is negative, then Q will be negative. The problem is that when we're looking at the formula Q equals ml, the product is always positive. And that does not make sense. Gaining heat cannot melt and freeze a material. For that reason, we need to manually add the sign for any phase change. And how do we do that? I want you to make this note before we begin the lesson, before we start taking down the examples. Place this note on your pink sheet, or in your notes, or in both. If there is a phase change, Q equals MLF or Q equals MLV, the object, if it's losing heat, the ML value is going to have to be negative. So if I go from liquid to solid or gas to liquid, the object is losing heat, which makes sense. If I have water and it's turning into ice, I have to take heat out of the water. If I've got steam, if I want to turn to liquid, I have to take heat away from the steam in order to turn it into a liquid. If going the opposite direction, so from a solid to a liquid, so if I'm melting something, or going from a liquid to a gas, so that means I'm boiling something, the object has to gain heat. So ML is positive. An ice cube at minus 4 degrees Celsius is added to 950 grams of 97 degrees Celsius water. How much did the ice cube weigh if the final temperature is 32.8 degrees Celsius? We always start questions the same way if we have two or more objects at different temperatures and they, given time, will be at the same final temperature. We always write down heat lost plus heat gained equals 0. Because in a closed system, heat is not able to leave or enter the system, so the heat gained by one object equals the heat lost by the other object. So I write down heat lost plus heat gained equals 0. Question is, what lost heat and what gained heat? Now, before we begin, I want you to write this off to the side of your example. It's going to be some pictures explaining what we're seeing, and we're going to add the variables in there. So first off, who was losing heat? Well, it's the water that lost heat because it decreased in temperature from 97 degrees Celsius down to 32.8 degrees Celsius. Now that's just a change in temperature, so Q equals mc delta T. Now I used the subscript of W because it's mass of water, specific heat capacity of water, and change in temperature of the water. And the change in temperature, it decreased by 64.2 degrees Celsius. Who gained heat? Well, it was the ice cube. The ice cube went from minus 4 degrees Celsius to water at 32.8 degrees Celsius. But it can't go directly from ice at minus 4 to water at 32.8. First, the ice would have to warm up to the melting point, which is 0 degrees Celsius. Once at 0 degrees Celsius, it could melt into water at 0 degrees Celsius, and then it could warm up to water at 32.8 degrees Celsius. So first, the ice warmed up, which is Q equals mc delta T. This time I'm using a subscript of I, mass of ice, specific heat capacity of ice, and change in temperature of the ice. And the ice warmed up 4 degrees before it started to melt. In the second step, the ice went from solid to liquid. So that is MILFW. Well, it's MLF, right? But mass of ice, and then the latent heat of fusion of water, because ice is water in the solid state. Then that water went from 0 degrees Celsius to 32.8 degrees Celsius, which is a change in temperature. So heat, Q equals mc delta T. In this case, that's the mass of ice, specific heat capacity of water because it's now in the water phase, and the change in temperature of, and I put IW for ice water, just so I can keep straight what each delta T belongs to. So the ice water went from 0 to 32.8 degrees Celsius, so it increased by 32.8 degrees Celsius. So our heat loss plus heat gain becomes MWCW delta TW plus MICI delta TI plus MILF plus MICW delta TIW equals 0. Now where did that come from? Well, our picture here, we said that the water lost heat, so the MWCW delta TW is what lost heat. And who gained heat? Well, it was the ice as it increased in temperature, and then it melted, and then it increased in temperature again in the form of water. We add that all together, that's going to give us a total of 0. Now I'm going to get all my MI terms to one side and my non-MI terms to the other side. And this is just like in math class when you're solving for x. You put your x terms on one side, non-x terms on the other. I'm going to put my MI terms on one side, non-MI terms on the other. And the only term that doesn't have an MI is the very first term. So I'm going to subtract MWCW delta TW from both sides. So on the left-hand side, they will cross out, and I wind up with MI terms on the left, non-MI terms on the right. Now, I'm going to take out MI as a GCF, my greatest common factor. So all the terms on the left have an MI, so if I take an MI out of each term, I wind up with this. Now to get MI by itself, I am going to divide both sides by that huge amount of terms in the brackets. So on the left-hand side, CI delta TI plus LF plus CW delta TIW will factor out. MI is all by itself, and it's equal to all that stuff we now see on the right-hand side. Now that MI is isolated, I will sub my numbers into the equation. Now kilograms and kilograms will factor out because kilograms is on the top and the other kilograms is on the bottom. We also have a degrees Celsius on the top and bottom in our numerator. If we look in our denominator, the very first term has a degree Celsius on the bottom and a degree Celsius on the top, so they will factor out. And same thing with our last term, the degree Celsius on the bottom will factor out with the degree Celsius on the top inside our denominator. I run it through my calculator. The only unit left in the numerator is joules, and on the bottom, all the terms have a unit of joules per kilogram. Now I will add all the terms in the bottom. And then I will divide top by bottom. Notice the joules and joules will factor out. And I wind up with 0.5319 kilograms. Now, how did I get kilograms in the numerator? Well, kilograms is in the denominator of the denominator. And if something's on the bottom of the bottom, that means it's on the top. Correcting to two significant figures, I wind up with 0.53 kilograms. Example 2. I have a 75 kilogram metal forging. They give us the specific heat capacity of the metal, which is 430 joules per kilogram degrees Celsius. And we're told that that metal forging is immersed in 710 kilograms of 32 degrees Celsius oil. We are also given the specific heat capacity of the oil, which is 2,700 joules per kilogram degrees Celsius. We are told the final temperature is 47 degrees Celsius, and we want to determine the initial temperature of the metal forging. I start by writing heat lost plus heat gained equals 0, because anytime I'm adding something hot to something cold and they reach the same final temperature, I use heat lost plus heat gained equals 0. On the side of your sheet of paper, we need to write A few little pictures here with our information. This will be our variable list of sorts. And who is losing heat? It's the metal. 75 kilograms of metal, and it's losing heat. And it's starting at some initial temperature we don't know, but we do know in the end it will be 47 degrees Celsius. Now that's a change in temperature, so Q equals mc delta T. The change in temperature, we don't know exactly what it's going to be, but we know it's going down. Now, the oil is what is gaining heat. So the mass of oil is 710 kilograms, and it starts at 32 degrees Celsius, and it's going to warm up to the final temperature of 47 degrees Celsius. Again, just increasing in temperature, so Q equals mc delta T. I use the subscript of O because this is for the oil. And the oil increased in temperature, so change in temperature of the oil is 15 degrees Celsius. So heat lost. Well, metal's losing heat, so that's mmcm delta Tm, and gaining heat is the oil, so that's plus MOCO delta TO, and that's all equal to 0. So what are we looking for? The initial temperature of the forging, which is the metal. So we're looking for Tim. Hey, Tim, where are you? So where is Tim? He's not inside of here anywhere, but it's the initial temperature of the metal. And we know that change is always final subtract initial. So change in temperature of the metal would be final temperature subtract the initial temperature of the metal. So that means I'm going to have to change delta Tm into Tf subtract Tim. Right? Why no M with the F, with the Tf? Well, that's because the final temperature is the final temperature. Everything's the same final temperature. But the initial temperature of the metal is different than the initial temperature of the oil, so that's why I have the metal next to the initial temperature. So Tim, temperature, initial, metal. Now to get it by itself, well, I got to start pulling stuff away from Tim, from furthest out, working my way closer and closer to him. Now the first thing I'm going to do then is subtract MOCO delta TO from both sides. So on the left-hand side, MOCO delta TO will factor out, and I now have MMCM in brackets TF subtract Tim equals negative MOCO delta TO. Now, next step. Well, before I get into the brackets, I'm going to have to get rid of the stuff that's outside of the brackets, which is MMCM. So I divide both sides by MMCM. So on the left-hand side, that will factor out. And I now have TF subtract Tim equals all that stuff on the right-hand side. Now again, to get Tim by itself, I'm going to have to move TF. TF is adding to negative Tim, so I'm going to subtract TF from both sides. So on the left-hand side, TF subtract TF, well, those guys will cancel out, and I have negative Tim. But I don't want Tim to be so negative, so I have to turn him into a positive. And I'm going to do that by multiplying both sides by -1. That means I multiply the entire left side and the entire right side by -1. Well, when the -1 goes into the brackets on the left, that turns Tim into positive Tim. And the -1 gets distributed into the brackets, so that means it's going to multiply by the first term, turning it positive, and multiply the second term by -1, which also turns TF positive. Now I've got Tim all by himself. Now I can sub my numbers in and solve. Now kilograms and kilograms will factor out. Joules per kilogram degrees Celsius and joules per kilogram degrees Celsius will factor out. So when I do this long string of multiplying and dividing, I will wind up with two significant figures. So 891.6 degrees Celsius plus the TF of 47 degrees Celsius. I add them together, I get 938.6 degrees Celsius. Now, the round off line goes where it goes because I'm adding and subtracting, and 891.6 was only good to the 10 spot, so my answer is only good to the 10 spot for significant figures. So the initial temperature of the metal was 940 degrees Celsius. Now I've got three 100-gram metal weights at 100 degrees Celsius, and they are placed in 100 grams of water at 35 degrees Celsius, and they attain a final temperature of 61 degrees Celsius. What is the identity of the metal? Well, we're adding something hot to something cold. They're going to become the same final temperature, so heat lost plus heat gained equals 0. Who's losing heat? Let's write this off to the side of our sheet. It's the metal. And it says the metal weighs 0.300 kilograms. Now, where did that come from? Well, I got three 100-gram metal weights, and three 100-gram metal weights weigh 300 grams. We convert that to kilograms by moving the decimal over 3 spots. And that metal is starting at 100 degrees Celsius, and it is going to cool down to the final temperature of 61 degrees Celsius. That is just a change in temperature, so Q equals mc delta T. And that metal decreased in temperature by 39.0 degrees Celsius. Who gained heat? Well, it was the water. So the water has a mass of 0.100 kilograms, and it started at 35 degrees Celsius and warmed up to 61.0 degrees Celsius. That, again, is just a change in temperature, so Q equals mc delta T, and the temperature increased in the water by 26.0 degrees Celsius. So who lost heat? Well, that was the metal, and the amount that it lost was mmcm delta Tm. And who gained heat? It was the water, and the amount of heat the water gained is equal to mwcw delta Tw. And of course, that has to add up to 0. To find out the identity of the metal, I will have to calculate the specific heat capacity and then look it up on the data table to see which metal is closest to the value I have calculated. So to get Cm by itself, the first thing I will do is subtract MWCW delta TW from both sides so that it will cancel out on the left, leaving me with MMCM delta Tm equals negative MWCW delta TW. Now, since MMCM and delta Tm are all multiplied, I will get Cm by itself by dividing both sides by mm delta Tm. So mm and delta Tm will all factor out on the left-hand side, leaving the specific heat capacity of the metal all by itself. And that's equal to negative MWCW delta TW over mm delta Tm. So I will now substitute my numbers in. I'll run it through my calculator, and I get 931.111. Three significant figures because every number I have, it has three significant figures, and I'm multiplying and dividing. Unit-wise, well, kilogram and kilogram will factor out, degrees Celsius factor out. That leaves me with joules per kilogram degrees Celsius. So the specific heat capacity is 931 joules per kilogram degrees Celsius. So I get out my pink sheet, and the closest thing to 931 is oxygen at 912. But it can't be oxygen because oxygen is not a metal. The closest metal to a value of 931 joules per kilogram degrees Celsius is aluminum at 900. So the identity of the metal, according to our calculation, is aluminum. Example 4, we have 200 grams sample of ethanol at 16 degrees Celsius being mixed with 200 grams of water at 85 degrees Celsius. Assume that there is no heat loss to the surroundings. What is the final temperature of the mixture? So again, hot and cold being added together, reaching the same final temperature, heat lost plus heat gained equals 0. We'll draw our picture off to the side. Who was losing heat? Well, it's the water. It went from 85 degrees Celsius down to whatever that final temperature is. It's just a change in temperature, so Q equals mc delta T. And we don't know how much the water is going down in degrees Celsius. And who gained heat? Well, it's the ethanol, because the ethanol was at 16 degrees Celsius, and it will warm up to, again, whatever that final temperature is. Just a change in temperature, so Q equals mc delta T. And the change in temperature is, well, we don't know that either. So heat lost, well, the heat lost is going to be MC delta T of the water. And the heat gained is going to be the MC delta T of the ethanol. And that will all be equal to 0. So I'm looking for TF, but where is TF? Because I don't see it anywhere. But I do know that change is always final subtract initial. So I'm going to have to substitute in TF subtract TI for each delta T. Now note when I do that, TF is TF because the final temperature is the same for everything. But the initial temperatures were different, and that's why I have TIW, which is the initial temperature of water, and I have TIE, which is the initial temperature of the ethanol. Now to get TF by itself, it's going to be a little bit of a long process here. I'm going to start by distributing MWCW into the brackets. That gives me MWCW TF subtract MWCW TIW. I will also distribute MECE into the brackets, giving me MECETF subtract MECETIE, and that's all equal to 0. Now I have two terms that have TFs. I have two terms that have no TFs. So I'm going to move my TF terms to one side of the equation, my non-TF terms to the other side of the equation. So I'll keep my TFs on the left-hand side, and I'll move non-TF terms to the right-hand side. So I'll start by adding MWCW TIW to both sides, so that on the left-hand side, the MWCW TIW term will cross out. The other non-TF term is the MECETIE. So I'm going to add that to both sides so that on the right-hand side it will cancel out. And then I wind up with this as a result. Now, again, I'm looking for TF. On the left-hand side, I have two TF terms. They both have a GCF of TF. So I'm going to take TF out of both terms. Now to get TF by itself, I will divide both sides by the MWCW plus MECE. And now TF is all by itself, and it's equal to all that stuff on the right. Now that TF has been isolated, I can sub my numbers in. I wind up with a unit of joules on the top. And that's because kilograms and kilograms in the numerator will factor out, and degrees Celsius and degrees Celsius will also factor out, leaving me with just joules. And that's true for both numbers that are being added. On the bottom, I wound up with joules per degree Celsius, and that's because in the denominator, kilograms will factor out and kilograms will factor out, leaving us with joules per degree Celsius. Now, in this next step, I'm going to be adding. In the top, I wind up with 3 significant figures because in those numbers I'm adding, the second number was only good to the 100 spot, 71230. That means that the numerator is only good to the 100 spot as well. In the denominator, both numbers were good to the decimal, so that means when I added them together, it was good to the decimal, and I now have 4 significant figures in my denominator. I'll divide the two numbers, and 3 sig figs divided by 4 sig figs gives me 3 significant figures. So I wind up with 59.5 degrees Celsius. Degrees Celsius because joules and joules will factor out, and I wind up with degrees Celsius on the bottom of the bottom, which means it is on the top. Be aware that not all questions in the assignment are mixing together two materials. So not all questions start with heat lost plus heat gained equals 0. Some ask how much heat is needed to be added or removed to cause a change in temperature, phase change, or both, a phase change and a change in temperature. An example would be, how much heat needs to be removed from 130 grams of steam at 124 degrees Celsius for it to become water at 12 degrees Celsius. So I'm starting with steam at 124.0 degrees Celsius, And as it cools down, well, if we look at the water line, we know that water boils at 100 degrees Celsius. That means it also condenses at 100 degrees Celsius. So the steam will cool down to 100 degrees Celsius, at which point it will start to condense and turn into water. Once it's in the water phase, it will continue to cool down until it hits 12 degrees Celsius. So the first thing that occurred was a change in temperature. So the amount of heat removed equals mc delta T. That's the mass of the steam, specific heat capacity of steam, and change in temperature of the steam. And the change in temperature of the steam, well, it went down 24 degrees Celsius. Then I had a phase change. That means I'm looking at LV. And note I put a negative in there. So mass of steam and LV of steam. And the negative because heat has to be removed from steam in order to turn it into water. Going the opposite direction, of course, heat gets added to water to make it boil. We're doing the opposite of boiling water, so that means heat has to be taken out of the steam to turn it back into water. And then I have another change in temperature as that water at 100 degrees Celsius is then cooled down to water at 12 degrees Celsius. So it's still the mass of steam because, right, the mass of the water molecules has not changed, multiplied by the specific heat capacity of water because we're now in the phase of water, and the change in temperature of water, which is negative 88.0 degrees Celsius. So Q equals, well, the amount of heat that has been removed is equal to mc delta T, subtract the phase change, and then the next mc delta T. And all these terms wind up being negative because when I substitute those change in temperatures, all the terms are negative. In order to cool steam from 124.0 degrees Celsius down to water 12 degrees Celsius, I'm continuously pulling heat out of the system. So I multiply all these numbers together, and I wind up with this here. Two significant figures, two significant figures, two significant figures. I stack them to figure out where my sig fig line is, and due to the middle number, which is only good to the 10,000 spot, that means that my answer is only good to the 10,000 spot, and I wind up with an answer of negative 350,000 joules, or negative 350 kilojoules, or negative 3.5 times 10 to the 5 joules. And that's the end of the lesson. You're good to start working on the H5 assignment.